Hello, this is Mrs. Davis. This is AP Pre-Calculus. We're working on Unit 2A review, and we're on free response question number 5. All right, so we have a table showing population of bacteria again in a blood sample of a patient. The number of bacteria present was observed over a 6-hour period in the table. So here's our 6-hour period. And first A says, what relationships exist between the time and the population? Okay, so we're just looking at the relationship. This is increasing and looks like this is also increasing. So we can say as time increases, the bacteria population increases. I don't think it wanted any more than that. Okay, use the model y equals ab to the x with these points 0, 60, and 176 to write an exponential growth equation. So we know we're going to have the bacteria at time t would be equal to the initial, which was 60 based on 0, 60. So 60 times b to the t. Okay, so to find b, we have 76 equals 60 times b to the 1, which is b. So b is 60 over 76, which is 19 over 15. So writing the function b of t, you would get 60 times 19 over 15 to the t. What is the value for the rate of growth in your equation from part B? The rate of growth is 19/15. Okay, and then it says, explain what this value represents in the context of the scenario. So that means we're going to look at the input and then the output, right? That's how we say it. So for every hour the blood sample is observed, the bacteria in the blood increases by 19/15. Sorry, sloppy. Bacteria per hour. Okay? Now, based on the exponential model from part B, what's the expected bacteria population after 12 hours if it's not treated? So that would just be B of 12. B of 12 would be 60 times 19 over 15 to the 12. Using your calculator, that's 1,023.527 bacteria. All right, let's go on to free response question number 6. Organized a little differently. This is right off of AP Classroom. We have a wind turbine using the power of wind to generate electricity. The blades make a noise. Okay, yikes. So at 0, the noise level is 105 decibels. At 100 meters away, it's down to 49. So the noise level can be modeled by an exponential function, and S of D is the noise level, and D is the distance in meters from the turbine. Okay, so part A says use the data to write 2 equations that we use to find the value for A and B. So it's sort of like the one we just did. But now remember, we do our work down here when they haven't left us a space, right? So A and part I says to write those 2 equations. So we can write 0.4 is equal to A times B to the 0. Nope, I'm not doing the wind turbine one. I got to do the right one. I'm looking at a different answer. This doesn't even make sense. Here we go, our 2 equations. Let's get our 2 points. It was 0, 105, and 149. Okay, does that sound better? Okay, so first A times B to the 0 equals 105, and A times B to the 100 is equal to 49. So how do we find the values of A and B? Well, anything to the 0, sorry, this is 2. Okay, it says find the values for A and B. So anything to the 0 power is 1, so A is equal to 105. Sorry. And then if we have that, 105 times B to the 100 equals 49. And so you can say B to the 100 is 49 over 105. And so the 100th root of 49 over 105 is equal to 0.9924. Okay. So we have our two A and B. So let's rewrite it. A is 105 and B is 0.9924. All right, so that was part A. Now says B. Use the given data to find the average rate of change of the noise level in decibels from D equals 0 to D equals 100. So we have to do the average rate of change. So average rate of change is equal to S of 100, right, from D to 100, minus S of 0 over 100 minus 0. Okay, and that's equal to 49 minus 105 over 100, which is approximately equal to, with your calculator, negative 0.560 decibels per meter. And that was the first part of B. And then the second part of B says interpret the meaning in context of the problem. So we're doing average. So we could say on average, as the distance from, so we're talking about the distance, right? From the turbine increases from 0 to 100 meters, the noise level decreases negative 0. Decreases, so don't say negative. Decreases 0.560 decibels per meter. And then the third part says use the average rate of change found in I to estimate the noise level in decibels at a distance of 120 meters. So they're wanting us to write the equation. So, M is going to equal negative 0.560. And if we use the point, let's see, 105, we can say that we have Y minus 105 is equal to negative 0.560 D. So writing it as S of D would be equal to negative 0.560 D plus 105. I kind of had a room on my page, but I'm going to put C now. Use the model to find the value of M such the noise level is 20 decibels. So 20 is equal to negative 0.560 D plus 105. And you're going to put that into your calculator. Is it 120? Yeah, 120. Oh, wait a minute. Find the noise level is 20 decibels at a distance. So, yeah, S of D I think I didn't do B all the way. Hang on. B says use that, interpret the meaning, show the work, and then C says use a model to find noise level is 20 decibels. Oh, we never did what it said to do at 120 meters for 3I. So then we'll have to say S of 120 equals negative 0.560 D plus 105. So that's approximately equal to 37.8 decibels. So we got that done now. So back to C, we're setting that equal to each other. And we're in a, let's see, we don't want the average. We want to actually find this, right? So S of D, so 20 is equal to 105 to the 0.992 to the M. Now that's because model S is given right here, right? So we put that back in. We have 105.992 to the M, and so then we set that equal. This would be Y1 and this is Y2, and we get M is equal to 206.448 meters. There we go. All right, I'll stop this video there.